All right, we're going to look at section 10.2 using these chi-square curves to check for how well something fits a pre-conceived distribution. So we're going to look at some observation of a population. We're going to take some sample of a population and look at its distribution over a set of categories. And then we're going to have some kind of an idea what we think the distribution should look like, some predicted values. And we're going to see, does it look like it's holding up? Now, again, things, because we're looking at samples and samples aren't 100% indicative of the actual population, it's not going to match perfectly. So, but just because it doesn't match perfectly doesn't mean we get to say, oh, it's not the same distribution. We're going to actually have to, make some kind of judgment using this hypothesis testing, just like we've done in the previous chapters and sections. So our null hypothesis will be that that the data does fit that predicted distribution, and the alternative will be that it doesn't. And so we'll be checking to see whether we should maintain that null hypothesis that it does fit the distribution, or whether we'll reject it and think they may have different distributions. All right, what we're gonna look at is, we're not comparing two different values and seeing how well they correspond, or two different categories. We're just going to look at a set of categories and how many observed values fell within that category that we thought should. Because of that, we're going to calculate this stuff maybe a little bit different than 10.1, but it's very similar. So to calculate the expected value for each one of these cells, we're going to say what percent did we predict for that cell based on the predicted distribution times the sample size, times n. Just a quick note, the sample size has to be big enough that the predicted values for each of these individual categories is at least 5. If you can't get at least 5 in there, then you're not dealing with a large enough sample to make a judgment call on this using this chi-squared values. We will calculate chi-squared in the same fashion as we did in 10.1, and that is using the formula. We're going to take our observed value minus the expected for each cell, each category here, square that, divide it by the expected value, and then we're going to add all those up, and that'll give us our chi-squared value. Since we're not looking at like two different characteristics and seeing if those are matched up, our degrees of freedom are just going to be, I'm getting ahead of myself, observed value and expected value. The degrees of freedom are just going to be how many categories we have minus 1. That's going to be the degrees of freedom. So it's not the sample size minus 1. It's going to be the different categories, and we'll see what I mean by categories, but it's going to be the number of categories minus 1. So not the sample size minus 1, number of categories minus 1. And again, just like we've done in the last, however many chapters, if your p-value comes out to be less than or equal to your level of significance, reject the null hypothesis. If it's more than that, don't reject the null hypothesis. Okay, so same old there. All right, so let's look at 645. Oh, and before I move on, I guess I should mention one of the things they talk about is, why are we doing a right tail test here with the chi-squared? And it's because we're trying to figure out how different they are, and the bigger the difference, whether it's below or above the predicted value, the bigger that difference is, the more likely these are different distributions, and we would reject the null hypothesis. So that's why we're looking we're basically measuring the differences, with some squaring and dividing to scale it, but we're basically figuring out the differences between the observed and the predicted. The bigger that difference is, the more likely we're going to be doing a rejection. So the more farther to the right we would be. Bigger difference, farther to the right. That's why we're doing a right tail test for that. Okay, so I just wanted to mention that. Okay, so let's look at 645. Now, the directions for the problems 5 through 16 in your textbook in this chapter actually begin on page 643. They have a list of things they want you to do, A, B, C, continuing on to 644 for D and E, okay? And there'll be special things for each problem as well, maybe. So make sure you do all those different parts for each one of these problems. So on 10, we're gonna have to do A, B, C, D, and E, and then there's also, it has a couple of its own things. So let's look at 10. Let X be a random variable that represents the average daily temperature in degrees Fahrenheit in January for the town of Hana, Maui. The X variable has a mean mu of approximately 68 degrees and a standard deviation of approximately 4 degrees Fahrenheit. A 20-year study, so 620 January days, that's our sample size, 620, gave the entries in the rightmost column of the table. So this right column over here, there were 14 days within that 20-year period that fell between 56 degrees and less than 60. There were 86 days that fell at least 60, but less than 64, and so on. You got those values. All right. Now, we have some expected values from the normal curve, so if this is a normal distribution, bell curve shape, then that's where these getting these values. So one of the things they ask on this particular problem on the next page here, remember that the mu is 68 and sigma is 4. So remember the mean is 68 and the standard deviation is 4. Examine figure 6.5 in chapter 6. Write a brief explanation for columns 1, 2, and 3 in the context of this problem. So let's real quick, if I look at page, let's see, 274, or sorry, 275, that's where you'll find that 6, does it say 6.3, 6.5? 6. It says 6.5, but I don't think it means 6.5. I think it means yeah, I think it means 6.3 actually, though it says 6.5. I think it means 6.3 because it's talking about this diagram with the normal distribution and the empirical rule. So if I real quick, I look at this here, category 1, that has to do with, okay, your values between from the mean down 3 standard deviations up to almost 2 standard deviations below the mean. And then the next category is 2 standard deviations below the mean up to about 1 standard deviation below the mean. And then the third category is 1 standard deviation below the mean up to the mean. And then from the mean up to 1 standard deviation up, 1 standard deviation to 2 standard deviations above the mean, 2 standard deviations, 3 standard deviations. And so since the mean was 68 and the standard deviations were 4, they just took the mean, subtracted 4 to get 64. They subtracted another 4 to get 60, subtracted another 4 to get 56. Likewise, to go up, they added 4 to get 72, added 4 to get 76, added 4 to get 80. And then according to that chart on 6.3, from the empirical rule, there's about 34% between 1 standard deviation below the mean up to the mean. Again, about 34% from the mean up 1 standard deviation. And then between 1 and 2 standard deviations either way, there's about 13.5%. And then between 3 and 2, there's about 2.35%. Now these values will be a little bit different if you use the Z table. This is just kind of estimates. They're just kind of estimating here. And then there's, about 0.3 or so % less than that. Now, sometimes people say something like this value is off the curve. Now, technically it will never be off the curve. But when someone uses a phrase like that, like it's beyond the curve or it's off the curve or something, that usually means it's beyond 3 standard deviations. 3 standard deviations is kind of like the cutoff of what is really expected. And then once you get a value beyond 3 standard deviations, like what's going on there? Well, we're not sure. It's something really unusuals happen in that case. So 3 standard deviations is kind of like the cutoff spot for any kind of acceptability. Beyond that, it's just kind of. So if you ever hear that phrase, it's off the curve or something beyond the curve, that's what it's referring to. Beyond 3 standard deviations, one way or the other. And you can think about like when we did those control tests, that if you ever got a value beyond 3 standard deviations, hey, things look like they're out of control. Whereas if you got something beyond 2 standard deviations, usually one value wasn't enough. You'd have to get a couple values beyond 2 standard deviations in close proximity with each other to say something was out of control. So anything beyond 3 standard deviations, usually beyond the curve, beyond the expected values. All right. Let's see. All right. So brief explanation. I would say something like, where did I put my little tablet here? Okay, let's turn that on. I would say something like, these use the empirical rule to set up the intervals based on mu and sigma. Okay, something like that. Little brief description. Okay, so for 2, use a 1% level of significance. 1% level of significance to test a claim the average daily January temperature follows the normal distribution. So we're trying to say, does it look like the normal distribution? Now, it's kind of funny. This should go into part A of the thing. I don't know why they add this own little thing here, but so let's go to A. On page 646. And A says, what is the level of significance? 1%. Okay. And then state the null and alternative hypothesis. So the null hypothesis will be the weather in January fits a normal distribution. And then the alternative would be it does not. Oh, maybe I said normal distribution with mean at, and I gotta move this, a mean at 68 and sigma at 4. And it does not fit a normal distribution with the mean at 68, the sigma at 4. It might be normal, but it might have a different mean, or it might have a different distribution or a sigma. So that's why I want to put those in there. It's not just that whether it fits a normal distribution or not, but it fits a normal distribution with those characteristics. B, find the value of the chi-squared statistic for the sample. All of your expected values greater than 5? What sample distribution will you use? What are the degrees of freedom? Okay, so a lot there. So I'm going to put B on this table, and I'm going to calculate the expected values here. Expected values, and I don't see I wrote it anywhere. I'm going to go ahead and put our sample size here. Sample size was 620. So I want to make sure I need that to calculate my expected values. And then I'm going to have down here chi-squared. I'm going to figure out what chi-squared is. So let me do the stuff I can do before I do all this calculation. And then, so find the value, or I'm not sure about that. What sampling distribution? The degrees of freedom. So degrees of freedom, I said was 1 less than the number of categories. So how is the data split up? How many categories? You think about a long time ago when we did like histograms and we set up different categories. That's basically kind of what this is going on. So how many categories do we have? 1, 2, 3, 4, 5, 6. 6 minus 1, we have 5 degrees of freedom. So 6 categories minus 1. All right. Are all of these more than 5? All these expected values. So let's calculate them. So I think if we get past the 2.35, then we're gonna good. And notice this expected value is symmetric, you know. So if I do the top half, I know what the bottom half is. All right, so turn this on. 0.0235 times 620, and that gave me 14.57. So this one down here has to be 14.57 because it's symmetry. 0.135 times 620, 83.7, 83.7, and then 0.34 times 620. So 210.8, 210.8. Okay. And then I'm going to figure out the values here that I'm going to add up for my chi-squared. So remember how we do that? We take the observed minus the expected squared over the expected. And then we're going to add all those up. Now, one thing about squares is this is actually also equal to the expected minus the observed squared over the expected. So, you know, just because of how my table is set up here, this one might work. I mean, just because you're squaring it, square it throws away the sign. So it doesn't really matter whether it's expected minus observed or observed minus expected, you know, whatever. As long as you're dividing by the expected value, that's the important part. It doesn't really matter what the order of the other two. So, right, so let's subtract that square, divide by 14.57. And again, since the expected values aren't real data values, you can get, you know, like how can I get 14.57 days of that temperature? Well, you know, it's either a day of that or not. I think I'm going to go to I'm going to go to 2 decimal places for this because the chi-squared table looks like it uses, well, sometimes it uses 2, sometimes it uses 1. Most of the time it uses 2. So I'm going to go to 2 decimal places when I calculate this. So 80 squared divided by 83.7. So looks like 0.06. And then we're going to go okay. So now you'll notice all these values so far are pretty small. That's actually a good sign that we're not going to reject the null hypothesis, because the bigger the chi-squared value ends up being, the more likely, the farther you are to the right, the more likely you're going to get a small p-value, because the farther you get there, the less space there is. And so the larger the chi-squared, the more likely you're going to reject it. So the smaller the chi-squared, the less likely you're going to reject the null hypothesis. And just looking down the line, if I had to guess, I would say this is probably not, come on. This is probably not going to get rejected is my prediction, but we'll see. 210.8. That is 0.08. And then 83.7 minus 83 squared divided by 83.7. So that's that's at 2 decimal places, 0.01. So 14. So this looks like 0.01 as well. All right, so add all those up, and that'll be our chi-squared value, 0.02. And looks like I got about 0.25, okay, for my chi-squared. So, getting back, were all my expected values at least 5? Yes. Yes. All these greater than or equal to 5. Way bigger than 5. So sample size is big enough. This would not work like probably for 1 year. If you just looked at 1 January, you probably, 30 days or 31 days in January, most of it in the middle, you might not get 5 days on these others. I mean, after 20 years, we only got 14 days in that low between 56 and 60 degrees. So, it has to be at least 5 for all categories. Got to be big enough. We're going to use the chi-squared distribution. Right? Chi-squared distribution. Okay, find or estimate the p-value of the test statistic. So, all right, so to find that, we're going to go to our chi-squared table, and we're going to use our degrees of freedom, which we said was 5. And we have about 0.25 a quarter, so 5 degrees of freedom, 0.25. Oh yeah, this isn't even on the chart, right? This p-value is greater than 0.995. It's not even close. It doesn't even get into the chart values. So for D, question D asks us, based on your answer to A through C, will you reject or fail to reject the null hypothesis? So the p-value is greater than this alpha value. Don't reject the null hypothesis. E, interpret your conclusion in the context of the application question. All right, so within this question, we would say something like, at the 1% level, we cannot say the weather distribution in January is not normal with mu of 68 and sigma of 4. So we can't make that claim. But it is not that distribution. And this is part of the problem with, I don't want to say a problem, but sometimes you'll hear like, okay, there's a bad hurricane or something. And it's like, oh, this proves that global warming or weather change and stuff. And then oftentimes you'll hear like the weather, meteorologists say, well, you can't really make that claim based on one storm. You have to look at the pattern, the data. And that's what's happening here is that, again, there's a certain distribution of storms that could happen, hurricanes, how many hurricanes we have every year, how strong those hurricanes are every year. And within that normal distribution, you can have extreme cases. You can also have very mild, we could have a year where we have 1 hurricane all year, and we could have a probability that we'd have, 500 hurricanes, multiple hurricanes every day, that hit the United States, for example. That is within the distribution. The question is whether it is so far off to one side that we could make the claim that it doesn't look like we're in that normal distribution anymore. And so it doesn't mean that we aren't. It just means that, maybe at whatever level they're setting, this right now isn't saying we've shifted far enough to whatever category or change in distribution from previous years. So just keep that in mind when you start watching stories in the coming summer, especially. You'll see things about storms and things, and try to listen to what people say. Is, you're going to have some people who are going to say, this is proof. We have bad hurricane, this is proof. But then you'll listen to meteorologists and they'll say, well, this could be a bad year, this could be proof, or this just could be an unusually large number of storms or strength of storms or something. Because they're looking at that distribution. They're thinking about that distribution and whether we have actually our mean is in a different location now, or it's still within that normal distribution of ranges. So that's part of the things that they use these kind of statistics for. All right, let me go ahead and have you do this. Problems 1 through 3. All. I don't know why I didn't say 1, 2, and 3. 1, 2, and 3. Do 5, do 11 and 15. 5, 11, and 15. Remember the directions for those start on the bottom of 643, and then there's also D and E at the top of 644. So make sure you go back and you do all those different parts. All right. Take care. See you later. And I will